Okay, I think we're ready to roll here. Okay, so section 2.3 is all about continuity, and we've talked a bit about this in the past. Like in pre-calculus, we talked about when things are continuous or not continuous, and so I wanted to kind of revisit that a little bit with you guys here. Kind of the basic definition of continuity, I think the easiest way to kind of think about it is something is continuous at a point if you can trace it with your pencil and not have to lift up your pencil to go over it, that sort of a thing. So we're going to talk about kind of the difference between that idea, being continuous at a point, and then having a continuous function, because they are two different things. Okay, so basically it's this. You have to have a few things happening all at the same time. So if the limit as x approaches a of f of x is equal to f of a, then f of x is continuous at a. And that means, and I said there's a couple of things going on there. So in this limit right here, that means the left and the right-handed limits are the same. So they're both pointing to the same place. So as you go from the right and you go from the left, they're going to the same place. And not only that, the function is defined at that same exact spot as the same thing. Okay? So it's not a situation like this. Like if I had a function with like a hole in it like that. Okay? Do you see how that fits just the left part of this? That yes, the limit does exist there, but it does not equal f of a, right? Because the actual point right here is missing. Okay, so if that were like a, like let's say here's my x-axis down here, there's a. So for that one, the limit as x approaches a of f of x exists, but it's not equal to f of a. Okay, because the function's not defined there at a. So if I wanted to evaluate that function at a, I wouldn't get anything for it. So it's not continuous at that point. However, if that were filled in, then I would be continuous there. Okay, because now the limit as x approaches a does equal f of a. Okay, as I come from the left and the right, yep, those are coming to the same place, and not only that little hole's filled in. It exists. Okay, so I can do f of a and get an answer, and it's equal to what that limit is. Okay, so that's how we're going to check for continuity at a point. And there are some different ways that we can not have continuity. Okay, that's what we're going to kind of investigate here first is what are the different ways that we could lose continuity at a point? Because usually we have it. Usually it's this nice, smooth, connected, function, that sort of thing. We see that more often than not. So it's probably easier to look at, okay, what are all the ways that that doesn't happen, and how do we recognize that? So this is something that we talked about in pre-calc a bit. So these should look a little bit familiar. We got these are discontinuities. So this is a jump discontinuity is one way. And in that case, we can lose continuity if we got a function that's going along and then it suddenly stops and then like jumps up to another value and then keeps going. It would look something kind of like that. So Can you guys think back to when we talked about all like those 12 basic parent functions in pre-calc? There was one that had a whole slew of jump continuities all over it. Remember what that was called? Yeah. The step function, right. So a step function has points of discontinuity all over it because every step is a jump, a jump, a jump, a jump. So, yeah, that's kind of the most, I think, recognizable function that has jump discontinuities in it. There's the removable. That's another one. And removable is actually kind of what I was talking about up here with the A stuff. I used an example of that. So for that one, you've got just a hole. And sometimes it's just the hole like that. There's just one missing point. Okay? So there's like a point has been removed from the function. Other times you've got the hole, but then maybe the point is like up there or something. Okay? So if the point is included and it's just like floating somewhere else, that just means your domain is covered. You've got every single point still in your domain. It's just not continuous at that particular point where it takes it out and puts it somewhere else. But that's what those generally look like. Some other ones that you guys have seen, infinite. These are probably the most common. And where do we see infinite discontinuities, do you suppose? What are these things that pop up in functions that as we're going along, then, oh, now we're going to infinity, and we can't keep going? Asymptotes, right. So some kind of vertical asymptote is in the way. So maybe we're going along, and then, oh, yep, we're caught. We can't get past this asymptote, and then the other side, it continues on, maybe something like that. Okay. So those come about. And then there's another one that is really rare, but still exists, so it's worth talking about. And that's an oscillating discontinuity. And these are kind of challenging to draw, so bear with me. But basically what happens with these is you've got usually some kind of a sine or cosine function has had something funky happen to it where it's going to oscillate back and forth between two numbers, but that oscillation, as you approach a certain number, is going to get more and more and more and more, and then it just goes nuts. And it just oscillates so much that it can't get past where it's at. So it keeps going back and forth, tighter and tighter and tighter and tighter and tighter, and then it cuts out. Hey.
With 3 students to go to that test.
Oh, hold on. Here, they're so. All right, sorry about that. So the oscillating discontinuity, like I said, it continues to oscillate so much that it gets caught and can't get past. Now, usually, you've got like the opposite thing happening, and then like on the other side, it'll do this same type of thing where it'll keep oscillating, and then it'll get caught, and then there's this like big mass of oscillation in the middle. So it kind of looks something like that by the time you're done. Now, like I said, those are really, really rare. But the idea is that it oscillates so much that it can't continue on, so it's discontinuous there. So those are the big four, but 3 of them are much more common. Okay, sorry. So these are the points of discontinuity, or different types. So if I give you a function, I might ask you then to identify where in the function is there a point of discontinuity. And so usually we need to know a little something about the graph of the function or how it's put together, that sort of thing, to be able to identify some of those. So let's try that a little bit. We'll take a look at some functions and see if we can identify where these things might come about. So, all right. So how about f of x equals 1 over x minus 2? This particular function has a point of discontinuity. So of the 4 that we talked about and what you know about these types of functions here, what kind of discontinuity do you suppose this one has? Infinite, right. Because we know 1 over x minus 2 has a vertical asymptote in it. Okay? And that's an infinite discontinuity. All right, so the graph of this thing looks something like this. So we would say for this particular function, there's an infinite discontinuity at x equals 2. So 2 is where we're having the problem. Okay, that's where we can't, keep going with the function without picking up our pencil. It doesn't fit the definition. The limit to the left and the right are not equaling the value of the function because there is no value of the function there. Doesn't work. Another one, let's do, and this one, there's going to be some of these where you're not going to be able to really see it unless you do it on your calculator. So this one I'm going to make a calculator-friendly question here. But what if we had absolute value of x divided by x? Take a minute on your calculator and graph that thing and take a look at it and see if you can identify what kind of discontinuity is going on for that one. Because I'm guessing you guys probably don't know what this one looks like offhand. All right, so if graphed correctly, it should look like this. Now, your calculator is not going to put the big open circles there, but we know they have to be open circles because this thing is undefined for x equals 0. Okay? But correct. Yeah, it can't include 0 at all, so neither piece has the 0 included there. But your graph on your calculator should have looked like 2 lines coming to the axis and stopping, right? When you did this one. So what type of discontinuity are we looking at for this one then? That's definitely a jump. Yep. So we got a jump discontinuity at x equals 0 for that one. Okay, so this is going to be kind of, with these, it's going to be kind of a mix of ones that you know what they look like that are non-calculator ones, okay, like the first one. Other ones that are a little bit more out there that you haven't seen that you can use your calculator for. But still, just being able to identify what type of point of discontinuity do you have going on, okay? So, that being said, now we get into this whole thing of, okay, we know continuity at a point. What does it mean to be a continuous function then? People often confuse the two, or they assume they're the same thing, and they're not exactly the same thing. So a continuous function, the definition of this reads as follows. It is a function that is continuous at every point on its domain. And the key phrase for this is on its domain. Okay? Because if there are points that are not in the domain, you could have points of discontinuity yet have a continuous function. If the point of discontinuity is simply not in the domain, then it could still be a continuous function. I'll give you an example of that. We'll go back to our reciprocal friend here. Let's just do 1 over x. What's the domain for 1 over x? Everything except for 0, right? Okay, so this would be a continuous function if it's continuous on this interval and continuous on this interval. Okay, so let's draw a quick sketch of what this thing looks like. So look at the function. Is it continuous on the interval negative infinity to 0? Yes, it is, right? That's this little piece down here. And there's nothing getting in the way of this little piece here. From negative infinity to 0, not including 0. So we don't have to worry about the fact that it never actually gets to 0. But this entire piece right here is continuous. Okay. Is it continuous on 0 to infinity? Yup, same thing. Over here, nice and smooth, continuous, nothing getting in the way over there. So, believe it or not, 1 over x is a continuous function. It fits the definition.
So would most functions that have infinite discontinuity be a continuous function?
Yes. Yep, infinite discontinuities. Oops, that should be is a continuous function. Infinite discontinuities, because they by nature take a number out of the domain, don't really affect if a function is considered a continuous function or not. Yep. The only ones you really need to be focusing on for this idea is, do we have any removables or do we have any jumps? Those are where we're going to have issue. Yeah, question? Oh, that means therefore. Sorry. Yeah, so therefore, 1 over x is a continuous function. Good question. I don't think I've shown you that before. Okay, so about an example of a function that isn't continuous then. Well, we talked about it before. The step function. And it looks something kind of like this. Okay, so and then et cetera, that way, and et cetera, that way. So what is the domain of that particular function? Everything, right? There are no x values not accounted for there. So, for this one then, same question. Is it continuous at every point on the domain? No, right? The domain is everything, but there are points of discontinuity at every integer as you go along on this thing. Okay? So, we have jump discontinuities at each integer, which are in the domain. So, therefore, int x is, should say is not a continuous function. Okay, so part of your work, what you're going to be doing is identifying what's continuous or what's a continuous function and what's not. So you got to focus on the domain. Okay, is that continuity at a point thing happening at every single point that's in the domain or not? Okay, and so those are some examples of the two ways that can go. All right. Okay, so making functions continuous. So sometimes we have a function that is discontinuous, and all it takes is one little change to make it continuous. So that's what we're going to focus on next. Okay, so got one I'd like you to take a look at here. Let's do x squared minus 9 over x minus 3. Now, on first glance, I bet most of you would tell me that this function has an infinite discontinuity, right? Come on, be honest. You look at it, it's got an x minus 3 in the denominator, and what do we always say in pre-calc? Whatever's in the denominator, that's where you find your vertical asymptotes, right? So it makes sense that you would have an infinite discontinuity here. But it's not the case, okay? Because it cancels out, all right? So factored out, this function is actually x minus 3 times x plus 3 over x minus 3. And these two factors cancel. So then we're left with f of x equals x plus 3. Okay, now, this particular function right here that we've created, I have to be able to use the original the same as this one, because they're supposed to be the same function, right? What number am I not allowed to use in this one? 3, which means because of the fact that this one came from this, I can't use a 3 in this one either. So what this looks like is kind of a little bit strange, but it looks like the line x plus 3 with a hole in it, because I can't use a 3. I can use anything but a 3, and it looks like this line. So the graph of this thing is, let's see, x plus 3. So it'd start up at 3, and it has a slope of 1, so maybe it's something kind of like that. But then when we get to 3 on the x scale, we've got to make sure we put a hole there, and then it continues on like that. So what kind of discontinuity are we looking at with this one, based on how that graph looks? I think I heard it. What kind is it? It's a removable. And another way of kind of thinking about removable, do you see how we removed a factor out of here? Okay, so that's kind of like removing that out of there. So kind of a way to remember it. But in any event, if I wanted to make this function continuous, I would just need to plug up that hole. So right now, what we've got is f of x equals x plus 3, where x is not equal to 3. But if I allow x to equal 3, if I plug up the hole, so to speak, then I can turn this discontinuous function back into a continuous function. Okay? So one of two ways you could do that. You could write this as a piecewise function. You could say, okay, f of x equals x plus 3 when x is not equal to 3, which is what we're already at. And then when x is equal to 3, make it equal to, that would be at 6, right? So make it a 6 when x is equal to 3, and now I've basically taken a little point and just dropped it in there and filled up the hole. Or, and this doesn't always work, but in this case it does, or we could simply say, well, just drop the x not equal to 3 then, right? That would technically still work, right? So for some functions, you're going to have to do this kind of idea where you just tell them how to fill in the hole. But for this one, because we had a formula that we know that if we just ignored this fact right here, this would work. It would fill in the hole and make this discontinuous function continuous again. So we could just write out, well, just x plus 3 would do it. It would just be that line then without that hole in it anymore. Okay, so the directions for these kind of questions might seem a little bit confusing. So I'll read what they're going to say, but it's doing this kind of process. It'll say, give a formula for the extended function that is continuous at the indicated point. Basically, take the discontinuous function, this one, and make it continuous. Okay, so fill in the piece that's missing. And usually it's just going to be figuring out where's the missing point and dropping one in there and just describing what you did. Okay. All right, last thing I want to touch on, and then I'm going to be done, is the intermediate value theorem. We're not going to use this a whole ton right now, but we will in the future, so I thought it would be good to at least mention it to you guys. Okay, so say we've got some function here. And let's say this function is on some interval. It starts and it stops. Okay, it goes from A to B. And then, so this value here would be f of A. And this value here would be f of B. And what the intermediate value theorem says is, if the function is continuous from A to B, no jumps, no holes, no asymptotes, okay, every point in there, every point between A and B is a continuous point on that function, then the function should obtain every value between f of A and f of B. Outside of that, maybe, maybe not, but definitely every y value that we can pick off between these two should be represented somewhere in that function. And in this case, if we kind of shine a light on that, between f of A and f of B, right here. Because if we're starting at f of A and we end up at f of B, we're going to have to go through those points in between to get there. Does that make sense? All those y values in between f of A and f of B, if there's no breaks, if it just continually moves, you're going to have to hit every single one of those points on your way from the one to the other. Now, you might go outside of this little corridor like we did here. We dip down a little bit, but to get up to f of B, eventually you're going to have to come through there, right? You can't avoid it. And we might even go up a little bit and then come back down, but you have to go through there to get up to that point. If it's continuous, it's going to hit every single one of those in there. Okay? So that's what it says. So here's how that is, like all written out in words, like your textbook has. It says a function y equals f of x. That is continuous on an interval A to B, and it's called a closed interval because we're including A and B. Takes on every value between f of A and f of B. Okay, so in other words, another way that this gets described is if I pick some y value right here, then the x that goes with it has to be between A and B somewhere. So we'll call it f of c. Okay, so if I pick some y value f of c and I come over, at some point between A and B, there should be that point C. That's caught in between. Cannot avoid it. That's the intermediate value theorem. So, like we will do a little bit more with that later, but show it to you now. When we get into derivatives and that sort of thing, this is going to become really, really important. But for now, just kind of have that idea in the back of your head. So, okay, I'm going to stop there to give you guys some time to work today.